Hello everyone, let's continue and conclude our discussion on CMOS inverter robustness. So in the last couple of videos, we proved on three different points about the CMOS inverter robustness, and this is the fourth one, which is the device variation on which we are trying to prove how inverter is robust or insensitive to the variations that it sees across. Okay, so in this case, we did a spice simulation for a strong PMOS and weak NMOS and tried to sweep the width of your PMOS and NMOS at certain intervals, and then we finally reached to a point where your NMOS was strong and your PMOS was weak, and we took all corner cases for your spice simulation, and now there are certain parameters that would need to quantify the CMOS inverter robustness. So in this case, there are two parameters mainly which we are looking for. One is the noise margin and another is the switching threshold. So let's begin with the switching threshold point. Okay, so for calculating the switching threshold, you need to draw a 45-degree line from this point till this point, and then identify those points on the curves at which your Vin is equal to V out. Okay, so in this case, if you observe this curve, this is the point, this is the switching threshold point. So for this curve, the switching threshold is roughly about point, I don't know, 0.2 volts maybe, and for this curve the switching threshold is about 1.4 volts. So there is about 1.2 volts of variation in the switching threshold, which is fairly acceptable to us. And the reason we say it's fairly acceptable is because, let's say if you design an inverter for this case, the shift in this particular, the shift, if the inverter was designed for a case where your switching threshold was supposed to be 0.4 volts, 0.25 volts in this case, and if due to the device variation the switching threshold shifts across this region, it's very less, even though because we have tested your CMOS inverter under this range of cases, and we see that the behavior of the inverter is intact. So the switching threshold varying in this area, it doesn't matter much to us, because we know that the inverter will still behave as an inverter and not as some other gate. Okay, similarly for this case also, if you try to build an inverter which is giving you a switching threshold of about 1 point, let's say 1.4 volts, and if because of the device variation that the situation shifts somewhere here and there, the shift in the switching threshold will be in this area itself, and we know it will behave as a CMOS inverter because we have tested the CMOS inverter for a wide range of voltages and for a wide range of devices, and we see the inverter behavior is intact. Okay, so that's basically the beauty of the CMOS inverter logic or the CMOS inverter design. The operation of the CMOS is kept intact. Okay, though there is a shift in the switching threshold at different points, but the shift is very minimal compared to the supply voltage that we have. Okay, and next is the variation in the noise margin. So if you look into the noise margin levels for this particular curve, the noise margin is 2.1, which is, or 2.5 minus 2.1 is, it's about 400 millivolts or 0.4 volts, which is large enough for us to gulp any of the high variation noise in the supply voltage maybe. Okay, and for this case, for the same curve, if you see, the noise margin is from 0 to let's say 0.3 volts, which is 300 millivolts, which is again good enough for us to filter out the low voltage noise variations or the voltage droop and the ground bounce kind of noise variations. So it's very easy to filter out those particular noise, and the inverter will behave as an inverter. Okay, so anything that lies between this range will be considered as a logic 0, and anything that lies between this range will be considered as logic 1. The good part is when you vary your device from the extreme cases, let's say from strong PMOS to weak PMOS and weak NMOS to strong NMOS, your variation in the noise margin is not big enough. Had the variation in the noise margin lied in this area, it would have been a problem for us, because any device which is lying in this area, you see the gain is so huge in this area, the device might shift. It's an undefined region, so your CMOS inverter behavior might be undefined. You never know whether anything that lies in this area will shift to logic 0 or move to logic 1. It's a metastable state. Okay, but the good news over here is that even though you vary your CMOS inverter to the extreme cases, your noise margin lies in the variation in the noise margin is low compared to if it had been in this area. Okay, so the variation is in the noise margin is from this point to this point, or it's about 2.1 to 2.4. it's about only 300 millivolts variation in the noise margin, and over here it's even less. It's about 0.2 to 0.3, let's say about 100 millivolts variation in the noise margin, but it's not huge. It's still under acceptable range. With that said, with all these parameters that quantify the CMOS inverter behavior, we still the CMOS inverter, the operation of the gate is kept intact. And that's the point that we are trying to make using the CMOS inverter robustness. So CMOS inverter is is not very responsive to the variations that it sees across itself. Okay, the operation of the gate is kept intact. You vary the supply voltage, you vary the device, you do all kinds of things, but your operation of the CMOS inverter gate is intact. And now this inverter can be used for different cases, for building of different complex gates. For example, you can use this inverter logic or this CMOS logic for building NAND gates, NOR gates, or any kind of gates. And that's exactly the point, that exactly is our point of discussion in our next course, which is circuit design and spice simulation dynamic. So we have been looking into, in this particular course, we have been looking into all the static analysis, the static CMOS behavior. In this case, we'll be actually looking into dynamic CMOS behavior. When I say dynamic, it's basically the waveforms or the signals will vary with respect to time. For example, when we calculated the rise delay and fall delay for a CMOS inverter, that's the dynamic simulation. And wherever we are dealing with voltage levels, that was about the static DCB, static simulation, or at time t. Now the dynamic simulations will be a varying function of time t. The waveforms will vary with respect to time t, and that's what will be our prime focus or prime agenda in the next course on circuit design and spice simulations. I would like to thank you all for listening to these videos. Hope you enjoyed watching these videos in the same way we enjoyed making them, and I will see you in my next course, in the next class on circuit design and spice simulations, on dynamic circuit design and spice simulations. So stay tuned, stay focused, stay hungry. Thank you.